Hello, Coach Travis here with another calculus video. So what we got here is we got a question, and the question is about a moving particle. So a particle moves along a line with a velocity v of t is equal to negative 2t plus 5, and that velocity is measured in meters per second. And we want to find the total distance, that the particle travels when the time ranges from time is equal to 0 to time is equal to 5 seconds. So, all right, so this is going to be a job for the net change theorem because we're trying to find a net change in the distance. And so the only thing that makes this thing tricky is that what we have here is we have the displacement versus distance problem. So what you have to remember, and I talked about this in an earlier video, that finding displacement and distance are related, but they're not the same thing. But they're very close cousins. So the moral is, like I said in the other video, that if you want to find the total displacement of a moving object over a time interval, you just do the integral of the velocity over the time interval. But if you want to find the total distance that's traveled as opposed to the displacement, then what you have to do is you have to find the integral of the absolute value of the velocity function. So since this problem is asking for the total distance, what we want to use is the net change, the distance version of the net change theorem. So that's the hardest part of this, I think. So no, that's right. This gets a little bit tricky. Once we set it up. So setting it up is pretty easy. We're just going to say, all right, it's going to be the integral of negative 2t plus 5 dt. And okay, but wait, not so fast. Since this is about distance, since this question is about distance, I need the absolute value signs around the velocity function. And then my integral is going from 0 to 5. Okay, so great. So that's the setup. So on one hand, I'm tempted to say, all right, so now all you have to do is evaluate that integral and you're good to go. But then what you should say is, whoa, wait a minute, Travis, not so fast. How do you find the antiderivative of an absolute value? That's not really, I don't feel like that's something we've spent a lot of time talking about. Do you just get to ignore the absolute value signs and just kind of pretend they're not there? And the answer, as you might guess, is absolutely not. So the idea here is we have to dig in a little bit to how the absolute value works. And what I mean by that is that, how does the absolute value work? Well, the way you think about the absolute value is, well, if the number's positive, it's just going to leave it alone. And if the number's negative, then it's going to make it it's going to change the sign. Because if it's negative, changing the sign will make it positive. So that's what I want to think about with this function right here. All right, so let's bring up GeoGebra to help us kind of understand what's going on with this absolute value function. So, all right, so right there on the screen, we got the graph of the absolute value function. So that is, or this particular absolute value function. So we have y is equal to the absolute value of negative 2t plus 5. That's the graph that we're looking at here. So the name of the game here is what we want to be able to do is we want to be able to rewrite this function so that we don't have the absolute value signs anymore. Because again, the idea is I don't know how to integrate something. I don't have any integral rules for dealing with this absolute value. So the trick to doing this is to notice that basically when you're dealing with an absolute value function, there are basically two functions. If I look at this, what I see is I see two straight lines. So I see that straight line that's highlighted in blue there, and I see this straight line that I've highlighted in red. And so if I'm sneaky, I can figure out, what I want to do is I want to figure out what the equations of those lines are. So if I look at the blue, and this is not a hard thing to do in this case. If I look at this blue line, I can see that, well, the y-intercept's at +5, and it looks like the slope is, if I go over 1, then I go down 2. So this blue part, let me see if I can write sideways. This blue part is y is equal to -2t plus 5. And the reason for that is, like I said, the reason for that is, well, the y-intercept's at 5, and the slope was -2. And now, if you're sharp-eyed, just say, hey, wait a minute, Travis, that's the same thing as this, only we just dropped the absolute value. And that is exactly correct because, I guess I'll say because when you graph this line, in fact, maybe I'll graph it. If you graph, let's graph the entire line. This entire line. If I were to graph this might be a little bit confusing, but I think you can figure it out. If I graph this entire line, what I get is it just goes on forever, right? It goes negative. And now, so as far as the absolute value is concerned, remember what the absolute value does? The absolute value doesn't change anything when it's positive. So on this part of the regular line, -2t plus 5, on this blue part of that line, it's positive, so the absolute value isn't going to do anything. So that's why it's legal to just get rid of the absolute values. But now, as soon as we get past 2.5, then we're in trouble. Because the absolute value it's going to take this negative number and it's going to do something to it. So at least for this part, for at least from as long as x is between 0 and 2.5, we can just pretend the absolute values aren't there. So let's write that. Let's do that with our integral. So our integral, we're integrating the absolute value function all the way from 0 to 5. And what we just said is, well, hey, as long as we stick in between 0 and 2.5, then this absolute value function is the same as if the absolute values weren't there. Actually, let me write that a little bit smaller. I don't want to run out of room. So this is -2t plus 5 dt. So we got that. So that's half the battle. But now we say, but the problem is now there has to be another integral, because you say, well, wait, what about this red part? How are we going to deal with that red part? Okay, well, let's see. That red part, that's the x values, or I guess the t values in this case, are going to be from 2.5 to 5 dt. And so now all we have to do now is figure out the equation of that red line. And so, well, let's think about this red line for a minute. Let's see, okay, what is the slope of this red line? Well, let's see, if I go over 1, then I go up 2. So the slope of that red line is a +2. And if I imagine extending it down here, I can see that, it's going to have a y-intercept of -5. So the slope of that, or not the slope, but the equation of that red line is what we got right here, -2t minus 5. So what I'm trying to say here is, in some sense, an absolute value function is like two functions put together. Whenever you see an absolute value function might be kind of scary. But really what it is it's just two functions put together. And what's interesting about those functions is they have a close relationship. Like notice what happens. Notice what happens if I take the negative 2t plus 5. If I take the negative 2t plus 5, and if when no one's looking, I put a negative sign in front of it, then notice what I get. I'm going to get a 2t minus 5, which is exactly what we got here. So the moral is an absolute value function is basically it's a join, it's a combination of two functions where the relationship between the functions is they're just negatives of one another. The blue graph is the negative of the red, and the red is the negative of the blue. And so anyway, for the purposes of our integral, then we say, okay, well, when t is between 0 and 2.5, we need to use the blue function. And then when t is between 2.5 and 5, then we use the red function, which is 2t minus 5. So now what we got here is we've got a way that you can deal with an integral that has an absolute value in it. Is you split it, you figure out where the function is positive, and that part just gets left alone. You just literally get rid of the absolute values. But then you have to figure out where that function inside of the absolute values is negative. And that part is going to get, the absolute value is going to put a negative sign in front of the function to get the second part. So that's how, but now I have two nice functions that I can find integrals of. So I don't know if I want to go through this whole computation with you. Maybe I'll take some shortcut, because I hope you could do it yourself from this point. The antiderivative of negative 2t is going to be, well, the negative 2 is going to stay there, and the antiderivative of t is going to be t squared, but the power rule for antiderivatives says you have to divide by the power, so we get 1/2 t squared, and then the antiderivative of 5 with respect to t is going to be 5t, and that gets evaluated from 0 to 2.5. And then we have to add, let's see, the antiderivative of 2t, the 2 stays there, the antiderivative of t is t squared, then power rule says we have to divide by 2, and then the antiderivative of negative 5 is negative 5t, and that gets evaluated from 2.5 to 5. And now you just plug in the number. Well, maybe I'll simplify it a little bit more before I plug in the numbers. But I don't think I'm going to plug in the numbers. If I simplify this a little bit, okay, negative 2 times 1/2 makes negative 1. So that's negative t squared plus 5. And that gets evaluated from 0 to 2.5. And then we add the integral. So yeah, at this point, I would probably just turn off the video and just figure it out myself, because it's much more fun to do it yourself than to watch me do it. It's boring watching me do basic calculations. I did the fun part with you, but now we're just doing the boring part. You should do it yourself. Okay, so that's what we got there. Oh wait, I see that I made a goof. I left out a t here. There we go. Okay, that looks good. So it turned, yeah, like I said, I'm going to skip this part here. I'm going to let you, I trust that you can do this. When you evaluate this, it turns out you get a 6.25. And when you evaluate that, when you plug in the numbers over here, you should also get a 6.25 into the red part. You also get a 6.25. Oh yeah, which if you look at the picture, that kind of makes sense. Because think about what you're doing when you do the integral. When you compute the integral, what you're finding is you're finding the area under the curve. And so if you look at this picture, the area under that line should be exactly the same as the area under that, because they're just two triangles. In fact, yeah, this was probably the hard way to doing all this work was probably the hard way to do this. What we should have done to evaluate these integrals was just look at the silly picture, because you just got a couple of triangles. You got that the base is 5. Well, I guess you got the base is 2.5, and you got the height is 5. And so if you figure out the area of those two triangles and you add them together, you get a 12.5. So all right, so 12.5 is our final answer. So yeah, that was kind of cool there at the end. That we see that we could evaluate if you got a nice function and you got a nice picture. You can always find integrals algebraically using the fundamental theorem of calculus. But if you got a nice picture, then you can find areas or you can find integrals just by using areas. But the moral of that story was that when you want to compute the total distance, you have to do the integral of the absolute value of your velocity function. And then that gets a little bit tricky. What that means you have to do is you have to figure out figure out the two pieces of that velocity function, figure out figure out the two parts of that absolute value function and split your integral into those two parts.